What we see around us is staggering complexity. How is it possible? Living organisms are created by chemistry. We are huge packages of chemicals. Now, what are the ideal conditions for chemistry? Well, first, you need energy. But not too much. What you want is just the right amount, and planets, it turns out, are just right because they're close to stars, but not too close. You also need a great diversity of chemical elements. And you need liquids, such as water. Why? Well, in gases, atoms move past each other so fast that they can't hitch up. In solids, atoms stuck together. They can't move. In liquids, they can cruise and cuddle and link up to form molecules.
Liquid water is just so good for getting evolution going. Molecules can dissolve in the water, form more complex chains.
Now, where do you find such Goldilocks conditions? Well, planets are great. And our early Earth was almost perfect. It was just the right distance from its star to contain huge oceans of liquid water. And deep beneath those oceans, at cracks in the Earth's crust, fantastic chemistry began to happen, and atoms combined in all sorts of exotic combinations.
Planet, microbes have adapted to survive the most hostile conditions. Arid deserts, the frozen Himalayas, in trenches under thousands of tons of pressure in the ocean deeps. In the vacuum of a space simulator, life forms have been flourishing for years without oxygen.
Very, very quickly, as soon as the Earth cooled off after its formation, we know that life began here.
because it happened quickly here on Earth, we think it's going to happen quickly on other planets as well.
We know that the galaxy is awash in water. It's awash in organic molecules and complex chemistry. All of the things that we know were necessary for life to begin on this planet exist in abundance throughout the galaxy. Did something similar to what happened on our own planet happen on those other planets?
There are more habitable Earth-mass planets in the observable volume of the universe than there are grains of sand on all the beaches on Earth.
other body of the solar system would indicate that the whole chain of evolutions, cosmic, chemical, and biological, is at work everywhere. In that case, the creation of life anywhere in the universe would be more the rule than the exception.
Within all of our lifetime, we're going to understand that there is life on other bodies in the solar system. We're going to understand the implications of that for evolution of life here on Earth. We're going to find planets around other stars that we can say we see potential signs of habitability in their atmospheres. That's all going to happen in the next 10 to 20 years. How exciting is that? We're on the verge of things that people have wondered about for millennia. Are we alone? And here we are on the verge of finding that out.
The universe is nearly 14 billion years old, and our galaxy is something like 12 billion years old. So there could be life out there that could be dramatically more advanced than the life that we have here on this planet.
The only elements that were created in the Big Bang were hydrogen, helium, and a little bit of lithium. All the stuff that makes your life livable, those elements weren't created in the Big Bang. The only place they were created is in the fiery cores of stars. And the only way they could get into your body is if the stars were kind enough to explode.
have any hope of finding alien life, we have to know what to look for. But where do we begin? How do we narrow down a seemingly infinite set of possibilities? There's one thing we know for sure. Nature will have to play by her own rules. No matter how strange alien life might be, it's going to be limited by the same physical and chemical laws that we are. On top of this, each alien environment will further limit what kinds of life forms can evolve there. Despite these natural boundaries, the possibilities are staggering to imagine. Trillions of planets, each a unique cauldron of chemicals undergoing their own complex evolution. To guide our thinking, this museum of alien life will be divided into two exhibits. Life as we know it, home to beings with biochemistries like ours, and life as we don't know it, home to beings that challenge our concept of life itself. Before we venture too far into the unknown, we have to ask ourselves, what if alien life is more like us than we think? If there's one feature that unites us with the other specimens in this museum, it's carbon.
Carbon is ubiquitous. It's one of the most common elements in the universe, and it's very good at forming large, stable molecules.
Carbon has the rare ability to form four-way bonds with other elements and to bind to itself in long, stable chains, enabling the formation of huge, complex molecules. This versatility makes carbon the centerpiece in the molecular machinery of life. And the same carbon compounds that we use have been found far from Earth, clinging to meteorites and floating in far-off clouds of cosmic dust. The building blocks of life, drifting like snow through the universe. And if alien life has selected other carbon compounds for their biochemistry, they will have plenty to choose from. Scientists recently identified over 1 million possible alternatives to DNA, all carbon-based. If we ever discover other carbon-based life forms, we would be fundamentally related. They would be our cosmic brethren. But would they look anything like us? If they hail from Earth-like planets, we could share even more in common than just our biochemistry.
What would life be like on other planets if it has evolved? Would it be like the world today here on Earth? Or would it be completely different? There are those who argue that from the argument of convergent evolution, if conditions on other planets are similar to here, then we would see very similar life forms. Animal and plant-like organisms that look very familiar.
On Earth, certain features like eyesight, echolocation, and flight have evolved multiple times independently in different species. This process of convergent evolution could extend to alien planets like Earth, where creatures face similar environmental pressures. It's no guarantee, but there could be certain universalities of life. The greatest hits of evolution on repeat across the universe. Each feature would be attuned to its local environment. Dimly lit planets would produce huge eyes to suck in extra light, like nocturnal mammals.
Some people have gone so far as to say that human-type organisms, humanoids, will occur on other planets.
The existence of other human-like organisms seems unlikely, given the long, convoluted chain of events that produced us. But we can't rule it out. If just one in every 100 trillion Earth-like planets produced a human-like form, there could still be thousands of creatures like us out there. Convergent evolution is also rampant in plant life, and C4 photosynthesis has arisen independently over 40 times. Would alien plants look like ours or something else entirely? On Earth, plants appear green because they absorb the other wavelengths in the sun's light spectrum. But stars come in many colors. And alien plants would evolve different pigments to adapt to their sun's unique spectrum. Plants feeding off hotter stars could appear redder by absorbing their energy-rich bluer light. Around dim red dwarf stars, vegetation could appear black, adapted to absorb all visible wavelengths of light. Earth itself may have once appeared purple due to a pigment called retinol that was an early precursor to chlorophyll. Some think that retinol's molecular simplicity could make it a more universal pigment. If so, we may find that purple is life's favorite color. Vegetation is more than just a curiosity. It's chemical information that could be seen from light years away. Earth plants leave a signature bump in the light reflected off our planet. Finding a similar signal from another world could point the way to alien vegetation. Perhaps this will be our first glimpse at alien life, a vibrant hue cast by a distant world.
What happens when you change the day length of a planet? What happens when you change the tilt of a planet? What happens when you change the shape of the orbit? What happens when you change the gravity of a planet?
Planets with long elliptical orbits would see drastic seasons. There could be worlds that appear dead for thousands of years, then suddenly spring to life. Most of the rocky planets discovered so far have been massive super-Earths. How would life evolve on these worlds? In the seas, gravity may not matter much at all.
A high-gravity planet isn't high gravity all over. If you're in the sea, and that's where all life starts, there's very nearly no gravity because you're much the same density as the stuff around you. It's when the animals come out on land that they feel the gravity.
High G-forces would necessitate large bones and muscle mass in complex life on land. They would also demand a more robust circulatory system. And plant life could be stunted by the energy cost of carrying nutrients under stronger gravity. Low-gravity planets would more easily lose their atmospheres to space and lack a magnetic field to protect from cosmic rays. But smaller worlds could be home to secret oases. Huge cave systems that provide hideouts for life. Possible habitable planets are estimated at 2.5% Earth's mass. If surface life does evolve on these worlds, it could be a sight to behold. Plant life could grow to towering heights, able to carry nutrients higher in lesser gravity. Without the need for bulky skeletons and muscle mass, animals could have body types that boggle the mind. Here on Earth, it took 3 billion years for evolution to produce complex plant and animal life. Simpler organisms are hardier, more adaptable, and more widespread. The largest collection in the Museum of Alien Life would likely be the Hall of Microbes. Yet finding even the tiniest alien microbe would be a profound discovery. bite-sized life could leave a big footprint. Like stromatolites on Earth, layers of microbes could build up into huge rock mounds over time, leaving behind eerie structures. And in big enough numbers, some alien bacteria could leave a distinct biosignature by exhaling gases that wouldn't coexist naturally, like oxygen and methane.
There's ways to make oxygen without life, there's ways to make methane without life, but to have them in the atmosphere together is almost impossible unless you've got biology making those gases at the surface. And it would have an imprint on the planet's spectrum of colors.
Next-generation space telescopes could find a signal like this on a world not far from home.
The closest Sun-like star with an Earth-like exoplanet in the habitable zone is probably only 20 light-years away and can be seen with the naked eye.
Most brown dwarfs are too hot to support life as we know it, but some are just cold enough. All the prime elements for life have been detected inside their atmospheres. And within these clouds, some layers would provide ideal temperatures and pressures for habitability. There could be photosynthetic plankton in these skies, kept aloft by churning upwinds. And with enough force, these upwinds could even support larger, more complex life. Predators. This raises a crucial question. What if we've been looking in all the wrong places? What if nature has other ideas? Most of the universe is too cold or too hot for liquid water and the biochemistry that supports life as we know it. But in case our biases are misleading, we have to cast a wide net to search for life outside the habitable zone, in places that seem wildly hostile to us. Exotic environments will demand exotic biochemistries, and while no element can match carbon's versatility, one contender is a frontrunner. At first glance, silicon seems similar to carbon. It forms the same four-way bonds and is also abundant in the universe. But a closer look reveals that these two elements are false twins. Silicon bonds are weaker and less prone to forming large, complex molecules. Despite this, they can withstand a wider range of temperatures, opening up intriguing possibilities.
Life based on the silicon atom instead of carbon would be more resistant to the extreme cold, providing a whole new range of weird forms.
But silicon has a problem. In the presence of oxygen, it binds into solid rock. To avoid turning to stone, silicon beings might be confined to oxygen-free environments, like Saturn's frigid moon, Titan. Its vast lakes of liquid methane and ethane could be an ideal medium for silicon-based life or other radical biochemistries. Without ample sunlight, beings on worlds like Titan would likely be chemosynthetic, deriving their energy by breaking down rocks. Such life forms could have ultra-slow metabolisms and life cycles measured in millions of years. High temperatures, typically rigid silicon-oxygen bonds become more flexible and reactive, triggering more dynamic chemistry. This has led to a truly bizarre proposal: silicon-based life forms that live inside molten silicate rock. In theory, these forms could even exist deep beneath the Earth inside magma chambers as part of a shadow biosphere. If so, then the aliens are right under our noses. Other shadow biospheres have been proposed, forms of life living alongside us that we don't even know are here, including tiny RNA-based life small enough to go undetected by existing instruments. Clouds of dust in empty space might seem like the last place you'd expect to find anything living. But when cosmic dust makes contact with plasma, a type of ionized gas, something strange happens. In simulated conditions, dust particles have been seen spontaneously self-organizing into helical structures that resemble DNA. These plasma crystals even begin to exhibit lifelike behavior, replicating, evolving into more stable forms, and passing on information. Plasma is the most common state of matter in the universe. If complex evolving plasma crystals really exist, and if they can be considered life, they could be its most common form. massive suns explode, some collapse into ultra-dense cores called neutron stars. Hulking masses of atomic nuclei crammed together like sardines. Conditions on the surface are mind-boggling. Gravity is 100 billion times stronger than Earth's. But beneath their iron nuclei crust lies something strange. A hot, dense sea of neutrons and subatomic particles. Stripped of their electron shells, these nuclei would obey entirely different laws of chemistry, based not on the electromagnetic force, but the strong nuclear force which binds nuclei together. In theory, these particles could link up to form larger macronuclei, which could then combine into even bigger supernuclei. If so, then this bewildering environment would mimic the basic conditions for life: heavy nucleon molecules floating in a complex particle ocean. Some scientists have proposed the unimaginable: exotic life forms drifting through the strange particle sea, living, evolving, and dying on incomprehensibly fast timescales. Life is not something that has to evolve naturally. It can be designed. And once intelligence is introduced into the evolutionary process, a Pandora's box is opened. Typical biological limitations, synthetic and machine-based life could be the most successful of all. It could thrive almost anywhere, including the vacuum of space, opening up vast frontiers unavailable to biological organisms. And compared to the glacial pace of natural selection, technological evolution allows exponentially faster growth, adaptability, and resilience. By some estimates, autonomous self-replicating machines could colonize an entire galaxy in as little as 1 million years. Can't predict how hyper-intelligent life would organize itself. But in theory, there could be convergent evolution at play. The electrical properties of silicon might make it a universal basis for machine intelligence, a redemption for its biological shortcomings. universe ages, perhaps machine intelligence will come to dominate, and naturally occurring biological life will be viewed as a quaint starting point. Perhaps we ourselves will lead this transition, and the great human experiment will be merely a first link in a sprawling intergalactic chain of life.
Isley has said that one does not meet oneself until one catches the reflection from an eye other than human. One day that eye may be that of an intelligent alien. And the sooner we eschew our narrow view of evolution, the sooner we can truly explore our ultimate origins and destinations.
The most complex object known in the universe is the human brain. These 86 billion neurons have given us the power to transform our planet. But is this the best nature can do? We now know there are something like 10 billion trillion habitable planets in the universe. 10 billion trillion chances for the brain to be eclipsed by something else. The search for intelligent life is more than just a scientific curiosity. It's driven by a deep desire to connect with something greater. Finding an alien civilization wouldn't just reveal we're not alone. It could chart a new course of evolution for our species. And unlike primitive life, alien intelligence could be detectable thousands of light years away, making them potentially easier to find. What do they know that we don't? And how do we make contact? We're not the first to wonder. 200 years ago, we dreamed of lighting huge rings of fire in the Sahara Desert to signal our presence. And in the 1860s, a French poet proposed a patchwork of giant mirrors reflecting sunlight to Mars in the form of the Big Dipper. But if you want to send a signal across an ocean of space, bonfires and reflected sunlight won't help you much. Even a nuclear war on a nearby planet would be virtually impossible to detect with current technology. To really get your message across, you need a form of light you can't even see. Radio waves are ideal for carrying information long distance because compared to other forms of light, they travel more freely through interstellar gas and dust. That's why SETI, the search for extraterrestrial intelligence, has focused almost entirely on scanning for radio signals, whether intentional messages or byproducts of technology. Our own radio transmissions have now traveled 100 light years and reached 75 star systems, some of which include potentially habitable planets. And if alien intelligence lies beyond this bubble of signals, they could still infer life on Earth by spotting oxygen in our atmosphere. Thanks to the SETI Institute and the recent Breakthrough Listen project, we have now scanned tens of millions of stars for signals. But despite all this, after 6 decades of searching, nothing. Only a series of false alarms and dead-end leads. We call it the Great Silence. But in reality, the search has barely even begun. There are 2 trillion other galaxies out there that are still too far away for practical study. If space were the size of all Earth's oceans, we would have searched less than a pool's worth of water for signs of intelligent life. On top of this, we might even be looking for the wrong thing. There's more than one way to communicate across space. An alien life might view radio as primitive technology. We have to consider every possible alternative, from the practical to the unimaginable. The search is now underway for a different type of signal, one we could even spot with the naked eye: laser light. High-powered laser bursts can outshine a star by thousands of times and can carry far more data per second than radio. We would have to be in direct line of sight to detect the beam. But spread across many light years, they would widen to encompass entire planets and moons. Fleets of laser beacons could be used to sweep the entire galaxy, like alien lighthouses in a cosmic sea. Thanks to a recent crowdfunding effort, plans are now in motion to monitor the entire night sky for laser pulses. But while these bright flashes would be relatively easy to find, advanced life might be using something far more elusive: neutrinos. Tiny subatomic particles that are streaming through you by the trillions every second. These ghost particles can pass through entire planets and not touch a single atom. It takes a giant room like this to detect just a handful of them per day. But researchers recently proved neutrino communication is possible by sending a simple message through 240 meters of rock. If advanced life is using them to communicate, their signals could travel anywhere, through any obstacle, at the speed of light. Their messages could be streaming through us right now, and we would have no idea. Or maybe intelligent life is taking an entirely different approach to communication, using space-time itself as a medium. By manipulating high-gravity objects, they could in theory create pattern distortions of space-time, which could ripple through the universe in all directions. But making gravity waves strong enough to be detectable would be extremely energy-intensive. Maybe they're up to something far simpler. Placing giant sunshades into orbit around a star could block out starlight in distinct patterns, like a kind of cosmic Morse code. And even though it might take years to blink out a basic message, a system like this would require little effort to sustain. But the most sci-fi possibility of all is that they have left messages in our DNA. Some have proposed that certain sequences of our genes could contain hidden messages, Easter eggs in our genetic code, placed by a life-designing higher intelligence. But far-flung scenarios like this are overshadowed by a more sobering possibility. Maybe we're just in the wrong place, at the wrong time. Using a detailed computer model of our galaxy, researchers have estimated that intelligent life was possibly most concentrated 4 billion years ago, and closer to the center of the galaxy. If true, then we would exist on the outskirts, light years away and billions of years too late to a galactic golden age. Maybe they were here millions of years ago, witness to a whole different planet. By now, they might all be long gone, and we could be living in a galactic graveyard. It may not be their signals that we find one day, but their relics. it turns out, our chances of finding an alien civilization depend heavily on their average survival time. If the average lifetime is something like 100 years, then they will blip in and out of existence, rarely overlapping, and our chances of finding one alive are slim. But if they survive for thousands of years or more, then our chances will skyrocket as the potential for overlap expands. But what if they're not communicating at all? There's still a way we could find them. We tend to assume that alien intelligence would share our motivation to communicate. But they may find the prospect of making contact too dangerous or too futile. If this is the case, then we have to get more creative in our search. In 2015, astronomers watched as this normal-seeming star began to dim in erratic ways, unlike anything they'd seen before. The cause is probably a giant dust cloud or a shattered moon blocking the light, but it has all the hallmarks of something else. An alien megastructure. And even though this explanation looks unlikely, it hints at a new way of finding intelligent life. Not listening for signals, but looking for their technology directly. Not searching for messengers, but searching for engineers. And to do that, we have to wonder, what mind-boggling alien technology should we be looking for? Each alien civilization would be wildly different, but classifying them by their energy usage will give us insights into what technology they might be using. The Kardashev scale divides them into 3 levels. Type 1 would have a mastery of their home planet, using all the energy available on it. Type 2 would have mastery over their star, harnessing all its solar energy. Type 3 would have mastery over their entire galaxy and would be more foreign to us than we are to amoeba. But before we go searching for alien super technology, how would we find civilizations like our own that have yet to reach Type 1? When a typical planet passes in front of its star, we see the starlight dim sharply. But observing a more gradual fall-off of starlight could be evidence of a dense ring of satellites, a Clark belt. Spotting this type of light curve wouldn't be a smoking gun, but rings around rocky planets are unusual, and it could point us in the right direction. Just as alien vegetation would leave a biosignature in its atmosphere, alien technology would leave a technosignature. Silicon produces a recognizable light curve similar to chlorophyll. Spotting this signal could point us to the presence of alien solar cells. And something more nefarious might also leave its mark on a foreign atmosphere. Alien pollution. certain pollutants like chlorofluorocarbons aren't produced by nature and could be detectable even in small amounts. These chemicals could even linger long after a civilization dies, pointing us to the remains of an extinct alien race. Such a discovery could give us crucial guidance on how to avoid our own extinction. And there's another universal hazard we would be familiar with. Any civilization that uses huge amounts of energy will produce huge amounts of waste heat. This excess heat could prove a serious threat, just as climate change does to us. But it could also leave a telltale signal. Finding waste heat radiating from alien planets or other regions of space could point the way to intelligent activity. If not exterminated by their own technology, some life forms may achieve total control over their planet and become a Type 1 civilization. With this mastery would come incredible powers. Control over all their world's ecosystems, its resources, and even its weather. But no matter how advanced, every planetary civilization will face the same cosmic threats we do. Gamma ray bursts, supernovas, and asteroid impacts will be a risk factor for any terrestrial race. Some might decide to flee to intergalactic space, reducing their exposure to existential risks, making their home in the voids between the stars. If so, then our search will have to encompass the entire swath of the universe. But alien life that decides to stay planet-bound will need long-term protection. The best way to protect your world will be the ultimate in home defense. A planetary shield. These shields would cause a telltale dimming pattern during transit and could also emit a detectable heat signature. Large-scale astroengineering like this would require a colossal amount of resources. And the easiest way to get them may not be from mining planets, but from mining asteroids. They are resource-rich and easier to manipulate because of their lower gravity. searching distant asteroid fields for temperature or chemical anomalies could indicate alien mining activity. Eventually, though, asteroids might not be enough. Since our civilization is so new, any other intelligent life is likely to be more advanced than us. So we should think twice before revealing our presence. But alien super civilizations won't just be looking for resources. They will also need staggering amounts of energy. Stars output billions of times more energy than planets receive. To harness it all requires building something truly mind-boggling. Dyson spheres are enormous megastructures that encircle a star, designed to capture its entire energy output. They could also double as vast habitats for life. A solid shell would be physically unstable, so instead of a sphere, we might find a cloud of objects, a Dyson swarm. No matter their design, they would generate an enormous amount of infrared waste heat. And they could also eclipse or even block out the star's light entirely. Dyson spheres could also be built around black holes, which could have a smaller radius and collect thousands of times more energy. Any beings that come to harness their star's entire energy output will reach the next level on the Kardashev scale. A Type 2 civilization. This level of mastery would imply an astounding capability. Star lifting is the practice of harvesting stellar material and could provide thousands of planets' worth of resources. This process would also allow you to lower the temperature of a star, postponing its death by billions of years. In about 1 billion years' time, our own sun will grow too hot for life on Earth. If we ever find evidence of star lifting, it could inspire us to one day do the same and prolong the game of life. Eventually, there may be life that outgrows its star and needs even more energy. To branch out across the galaxy, life forms this advanced will probably need near-light speed travel. And if they do have this capability, there's a chance we could catch them in the act. alien starships that hit the brakes at light speed could leave behind a long trail of ionized gas. These trails might emit detectable infrared radiation. Strokes of light painted by masters of the universe. Once life forms have harnessed all the energy their galaxy can provide, they will achieve unimaginable power. A Type 3 civilization. This cosmic virtuosity would be totally unfathomable to us. Life that has built billions of Dyson spheres and can create stars at will. In theory, their thirst for energy could make a whole galaxy go dark. So one way to search for Type 3 life forms is to look for what's not there. In distant space, there are huge voids between clusters of galaxies where no light emanates. These voids were once thought to be evidence of advanced life having harnessed the energy from every star in the region. But it turns out they are naturally occurring features of the universe. And a recent analysis of nearby galaxies revealed no evidence of any galactic-scale civilizations. In theory, cosmic architects could assemble enormous planetary systems far more intricate than anything nature could produce. One possible system that would be gravitationally stable involves 9 sun-like stars orbiting a supermassive black hole, which could support 550 Earth-like planets in a habitable zone. These artisanal solar systems could make ideal long-term habitats, or could even function as an alien nature reserve, with each planet hosting a different strain of life. It's hard to imagine any life forms more advanced than this. But in theory, there could be beings that control or created our universe itself. Researchers are beginning to test the idea that reality itself is just a simulation, or an experiment run by some higher order being. Anything this advanced would transcend our ideas of life itself, as they would exist outside of time and space. In a way, the search for intelligent life is an evolution of the age-old search for God. Both are driven by a longing for truth and connection with something bigger than ourselves. And what if we do find a signal one day? What happens when the ancient dream becomes a reality? Just knowing they're out there would profoundly change how we see ourselves. For the first time, we would feel a true sense of cosmic brotherhood. And studying their messages or technology could lead us to huge advancements and help secure our own long-term survival. But the possibility of meaningful two-way communication would be bleak. Separated by hundreds or thousands of light years, we would be studying these civilizations as they were in the deep past. And our experience of language could be entirely foreign to them. But what if, after all our searching, we never find another sign of intelligence? What if we really are alone? We can never be truly sure, as there will always be distant galaxies too far to ever study. But never finding any evidence would mean that our place in the universe is truly unique. It would saddle us with an immense responsibility to keep the flame of intelligence alive. Just as ancient civilizations speak to us through their monuments, we could build monuments of our own for future life to discover. Cosmic time capsules preserving a record of our achievements and our knowledge. Perhaps other races will do the same, and these memory vaults could become connected over time, each new civilization adding a link. It could be our destiny to be the first link in this chain, to be the founders of a galactic encyclopedia built upon by future life forms we will never meet.